So hello everyone, this is an optional example to help hopefully clarify the concept of confidence intervals. And we're going to use the example of tabletops again. There's no slides, I'm just going to write here. Of course, I use tabletops because when you're in a classroom, it's always much easier to point to the desks in front of you. But I just read an article about the tabletop company that produces the very high-tech tables for the Apple retail stores. And they are made with a lot of precision, and so maybe the tabletop example is actually not so bad. But our little humble tabletop factory makes tables, and we have a random variable, which is the width of our tabletop, and we call that x, and we know that this is normally distributed with a mean and a variance, and we know that our table runs at a mean of 80 centimeters, and we have a variance of 9 centimeters squared, or a standard deviation of 3 centimeters. Now, I know this would mean their tables have quite a lot of variability in them, but for the sake of this example, we'll just leave it like that. Now, we have a customer that comes along one day, holding this briefcase, and the customer says, I would like to have tables. I need a tabletop supplier who can supply me with tables that are on average with a width of 80 centimeters. On average, the tables have a width of 80 centimeters. And we say that's no problem. Our factory provides tables, and we are centered around a mean of 80 centimeters for the width. And the customer says, well, that's fine, but I'd like to take a sample of 4, n equals 4. And so he takes a sample of 4 tabletops. And the first tabletop he measures 79 centimeters. And the second table he measures 78 centimeters. And the third table he measures 83 centimeters. And the fourth table he measures 84 centimeters. You take the average of all of those and you get a sample average X bar of 81 centimeters. Now, he knows that we don't run an absolutely perfect process. He knows that there's variability in our process, but he looks at that value and he says, I am looking for a supplier that can provide me an average tabletop width of 81 centimeters. So what do we do? And this is where the confidence interval comes in handy. We learned in the lecture that we can construct a 1 minus alpha % confidence interval by taking the sample average plus or minus a constant. And this constant is equal to a value c, so c for Charlie, times sigma over the square root of n, where sigma is the standard deviation. Here 3 centimeters, and here we have a sample size of 4. Now, what does all this mean? First of all, this is day 1 when the customer comes. Day 1, he measures 4 tables. He gets a mean value of 81 centimeters. On day 2, the customer comes in and he measures another 4 tables. And does he get 81 centimeters again? Most likely not. Maybe he gets 81.3 centimeters. Day 3, he comes in, he measures 4 more tables, maybe he gets 79.7 centimeters, and so forth. Every day that the customer comes in, he's taking a sample of a random variable, which means that the sample averages that he measures every day are also random variables. So every day he comes in, and every day our poor customer is not satisfied. He never sees a long-term average of 80. So how can we use our confidence interval to go back so that on day 1, our customer is convinced that our line is running on target with a mean and average of 80 centimeters for all of our tables? Well, first thing we need to do is we need to give him a level of confidence. So we choose our confidence interval, our 1 minus alpha %, to be a high value, say 95%. This means 1 minus alpha is equal to 0.95, or alpha is equal to 0.05, or 5%. So a small value of alpha for a larger confidence. And typical values are, of course, alpha equals 1% or 5% or something like that, 2%. So the next thing we need to do is to identify the C value. Where does that come from? Well, it actually comes from the alpha that we've chosen. So C is our choice. And if you go back to your standard normal, our standard normal distribution, which had a mean of 0 and a standard deviation of 1, what we're doing is we're looking for the constant plus and minus C, where the probability of that the random variable Z would lie in the shaded region, let's say that, would lie beyond plus C or below minus C. You want that to be alpha over 2. So in this case, 0.025. And here, alpha over 2 equals 0.025. So in total, that you have 5% probability of lying outside those C values and 95% of a probability that your Z value would lie within those tables. So you have chosen this 95%. You have chosen what that C value is, and you can look that up for an alpha of 0.05, and you find that C, so C as in Charlie, is equal to 1.96, and that's almost 2. So again, we've kind of learned that if you're 2 standard deviations above and below the mean, roughly 95%, there's a 95% probability that your random variable will lie within those 2 standard deviations. So we can now finish constructing our 95% confidence interval for the mean using our day 1 value is going to be x bar plus or minus k. And this is going to be then 81 centimeters plus or minus 1.96 times 3 over the square root of 4. Can you read that? 1.96 times 3 over the square root of 4. And when we do that, we're going to get 81 plus or minus 2.94, or 78.06 and 83.94. Okay, 83.94. So, what does this mean? The customer has come in. He measures an X bar in day 1 of 81 centimeters. This is a random variable. We give him a 95% confidence interval. This means we need to find a constant value from our tables of 1.96. We can then construct a 95% confidence interval equal to 78.06 and 83.94, and this means we are 95% confident that our true mean, our population mean, lies within this interval. Sorry, my writing's very messy with the pen. But we are 95% confident that our population mean lies within this interval. So the day 1 when the customer comes, we take our measurements, and instead of going away unhappy, we say, dear customer, look, our confidence interval contains 80. We can be 95% confident that the true mean lies within this interval. Now, whether he's happy or not is another question. But what else does this mean, this 95% confidence interval? It means that on 19 days, so down to day 19, the customer can come in and we will construct a confidence interval around the mean, and 19 out of 20 days, because 19 out of 20 is 95%. On 19 out of 20 days, the true mean will lie in that interval. So he will see an interval that contains the value 80. But on one day, our interval will not contain the true mean. So I hope that clarifies a little bit how we could use the confidence intervals. And of course, you can see, and there's an exercise about this, if you want to change your confidence interval, how could you make it more precise? Well, you could increase the sample size. You can decrease the variation in your production, which is, we really should do here for our tabletops. And you can also mess around with the 1 minus alpha % that you're telling the customer. If you choose to change the alpha value, you can also affect your C value. Okay, thank you.